Hello, everyone, and I'm here today to talk about MLCube. And MLCube is one of our big efforts coming out of ML Commons. And I'm Victor from the Best Practices Working Group. I co-chair this with Diane, and I'm here to talk about one of the key pieces of things we work on. And this is brought to us by all sorts of members of ML Commons from across the industry. So I'm just going to share what we've been doing and the problem we're trying to solve. And the problem we're trying to solve fundamentally is that ML is too hard. And in particular, the friction we're trying to remove comes from using a model you found. Like if you go to GitHub and you see someone else's model and you want to run it, chances are you're going to have to book an afternoon to read through their README, to download their data, to figure out how to pre-process it correctly, to copy and paste their commands, to figure out why your version of NumPy conflicts with their version of NumPy, to build a new Python environment. It is a lot of work. And this is the core problem we see, especially in ML Commons, where we do a lot of benchmarking, where we have a lot of different community members sharing models. We lose innovation because people don't want to run models they find because they know it's going to be work. They know they're going to have to dig through that README for a long time. And they're going to have to track down the data set. And then they're going to find out that they don't even have the right version of CUDA to run it in the first place. So this is a huge difficulty that we all feel. And we want to make it easier to run other people's models, to reproduce their experimental results, and to reproduce their benchmark results. And to do that, we are looking at a simple solution. So on one hand, you have all of the complicated infrastructure and products and services that go into running AI. This is your experiment framework. This is your cloud solution to deploy AI models. This is your cluster scheduler that your researchers are all using to submit jobs to. This is, your local dev environment. All of these things put together make this huge, complicated set of infrastructure that has to work with AI, and they all have their own intricacies, and it's a huge, huge space. On the other hand, you have all the technology that goes into driving a model and driving the actual training and inference. These are frameworks like PyTorch and TensorFlow, supporting libraries like SciPy and NumPy, and all of the other dependencies like image libraries that go into it, all of the other things that are required to actually train the model, all of the special libraries that you go through, the compilers, all of that. And what we're looking to do is have these two ends work together simply and efficiently by decoupling them and allowing them to interface using a simple, low friction interface. And so that's the key behind MLCube, is we're looking for something really simple that allows us to decouple these difficult problems and these very complicated spaces. So we're not here to change what's being done in either of these areas. We're here to simply provide a simple way to separate the people who make the models from people who have to run the models. So that way they can work together efficiently and effectively. I think of this as a metaphor, right? It's a shipping container, and it allows you to plug and play models from anywhere you find them. And the interesting thing about a shipping container is it's boring. It's simple and it's boring, and yet it is used all around the world. And the primary thing that makes this interesting, what really is a selling point of a shipping container, is it doesn't have opinions and it is dirt simple. That's the thing. Container ships work because everything is the same size and shape on them, and they don't have to worry about how do we pick up this basket of bananas versus how do we pick up this, box of iPhones, right? They're not different objects you're dealing with. It's not all unique. everything becomes uniform and easy to work with. And that is the key to what makes all of the complicated logistics of shipping and moving things around in the real world work. And it's the same thing we're doing for AI, is simplifying the logistics of how to move models around. So I'm going to talk about MLCube today in some technical detail. And the things I'm going to really emphasize are what an MLCube is. And we're going to talk about from both a not just metaphor perspective, but concretely what it is. And at a high level, you can think about it as a Docker or an OCI image combined with a simple file system interface. So a simple way to talk to that image and the metadata that makes it possible. We're also going to talk about execution of an MLCube. So not just what it physically is, but how it actually executes. And an MLCube can run in a lot of different environments, basically everywhere Docker is supported, or another container image is supported. And we already have examples in our working group around local execution, Kubernetes execution, and cloud-based execution. And I also want to talk about an interesting project we're working on right now, which is showing how MLCube works in the federated space. We didn't start out looking at the federated programming space for MLCube, but it turns out the simple thin interface and the shipping container model works really well there too. So we're going to talk about some partnerships and efforts we have going on in that space, which is really interesting. So, besides being this mythical shipping container, what is an MLCube actually? And first and foremost, it is a Docker image that is pre-built that you can download and pull. So you get the real image. A Docker file is great. And some use cases you want the Docker file. But what makes MLCube awesome is that you get the built image, because there are so many times where you pull a Docker file and it is 6 months or a year old, and the code is still great, but it needs a dependency on Ubuntu and the repository is shifted, or the pip package is no longer compatible, or it can't download a certain RPM. This happens all the time. And then you're stuck because you have a broken Docker file that you're trying to debug. I don't like debugging broken Docker files, and I don't know anyone who does. And that's oftentimes people eventually just give up. So it is a built image that you can download and run. It is also has the appropriate platform information. This includes accelerator information of what's needed, whether it's GPU, TPU, whatever accelerator you need to go. It describes the memory that is needed. What are your memory requirements? Some models need a lot of memory, some models don't. It also describes like disk. If you're downloading a big data set, you want to know ahead of time, you're going to need to free up some space. And the other thing we're going to talk about is a task. And a task is an operation or what your model does. This could be training, this could be inferring, this could be pre-processing a data set. And the basic intuition, will go into more detail of a task, but the basic intuition is that it's going to read it from the file system, do work, and then write back to the file system. So right now we're looking at some of the metadata that we talked about that describes the platform. In this case, we're looking at effectively what kind of computer you'll need to put together to execute the model. And this is it, right? Like, you can go into a lot of detail describing a computer. You can say how much L3 cache you need and what bandwidth of memory you need and how much throughput you need on your network. You can characterize all these different parts of the system. We keep it super simple and as minimal as possible while still getting things off the ground. So like, do you need the internet? How much disk are you going to need? What kind of accelerator do you need? This is kind of the core starting point. And this is the intuition of, I'm pulling this model off of GitHub. I'm going to make an AWS instance to run this, so I'm gonna run this in cloud, what do I have to put into that form when I'm creating my instance? What do I have to put there to make sure I can run this model? Because I don't want to have to like, go provision my computer and then find out I don't have enough memory and the thing crashes. So that's the intuition here, is what do I need to provision to run this model in its entirety? So let's talk a little bit more about a task. So now that we have the right computer set up, a task is tied to the file system and goes through files and directories. So here we're looking at a training task, and you can see the input is going to be a data set and parameters, and this parameters is a file. And now this might not be familiar to some people. Some people store the parameters files. Some people like using the command line. This is a parameters file, and I'll get into detail why it's a file and not just a set of parameters on the command line. And you do your training, maybe it's in PyTorch, maybe it's in TensorFlow, maybe it's in some other new framework. And then you produce a model and you produce logs, and those go back to the file system. And so the thing I want to call out is that the inputs are going to be read-only, and the outputs are going to be write-only. And this is a really important observation, because this means that you're going to have idempotency. You're going to be able to run the MLCube again on the same inputs, and you'll have, to the degree which AI is deterministic, which is another discussion. But as far as the model can provide, you'll get the same output. And this is sometimes true for some models. Some models, will modify their inputs, but this is a really powerful property for anyone who wants to build workflows, or anyone wants to actually build infrastructure on top. So we provide this for all the infrastructure that works with AI models. This ability to make the assumption that what's going in is read-only and what's coming out is write-only is extremely powerful. And the other thing I want to call out is, in these workflow scenarios, like let's say you're going to download data, let's say you're going to pre-process the data, then we're going to train the data, and then we're going to infer with the trained model. In this case, you can think of this workflow as effectively the outputs of one task become the inputs of the next task. So we're basically daisy chaining these tasks together into a workflow. And we'll talk more about the stack later, but we're not really, as our work is not in making workflow managers. There's a lot of fantastic products and services out there that do AI workflows. We're not here to make yet another workflow manager, but we're here to make sure that MLCube can be used in workflows for the workflow managers that want to use it. So let's look through a task. We talked about it at the abstract level, but a task, when you actually fill out your metadata, is going to be a task. And in this case, we're going to get a pre-processing task, and you have your inputs, which are you're effectively going to declare a signature for this. So it's going to be the raw data, which is a directory, and it's going to produce the pre-processed data, which is another directory. So this is a task that directory goes in, new directory created on the way out. And then when you train with that pre-processed data, you're going to take your data in, you're going to take your parameters file in. And again, this is a file of parameters, so this will have your batch size and your learning rate and all that important information. And out of that is going to come the model. In this case, it's a directory with a checkpoint. Some models might produce files instead as their checkpoint or output, and a log describing what happened. So if you're going to make an MLCube and have an MLCube constructed, assuming you already have some familiarity with Docker, it's a pretty three-step process. You have to make sure the main file expects to use the MLCube interface, which is going to be passed, here are your file paths to read, here are file paths to write, and then here's the task to execute. So assuming you have a main file that takes that information and then reads the appropriate files, calls your model main function. It's kind of a thin wrapper you put on top of the model. You upload your Docker image to a repository, and then you fill out the simple YAML metadata we just went through, and you have yourself an MLCube. So this is fundamentally how easy it is to put together an MLCube, and this should only take, less than an hour if it's your first time doing it and you have familiarity with Python and Docker and everything. It's a pretty straightforward process, and most of it can be automated in a pretty simple way. Now that we have our MLCube, we're going to look at how it's executed. So we've been talking about what the person does who's publishing the model. If you're going to put the model out into the world, I've been talking to you. Now, if you're the kind of person who's going to take the model and run with it and do something with it, let's look at what that looks like. And so as we're running this MLCube, the basic user flow is pretty simple. You get your cube from GitHub. So in this case, we're pulling a model out of GitHub, and this is going to be a MLPerf training benchmark for SSD. And you're going to get our reference runner. So this is our reference implementation of MLCube execution. So this is going to let us run the MLCube. We'll go into more detail of what this actually is, but you'll effectively call it on and point it at your MLCube. And then this will do that train task that'll take in the data, produce the model. So let's look behind and underneath this to see what's going on. And effectively what happens is you write your inputs. So this is going to be, you go edit your parameters file and you make the batch size bigger, or you change the learning rate. And then you pass that off to the runner. And so the runner will get the paths of the files you want to work with, so your parameters file and your data set, the path to the MLCube, and the name of the task, which is train. And the runner will go out to the internet and it'll pull down that Docker image for you. And then it'll invoke that Docker image, pass it the files it needs, and a task you want done. And then the main file we talked about, what that'll basically do, read the inputs or hand it off to your existing model main function if there's an existing model you're using. And it will basically let the model run, produce the right outputs to the file system. This is all being done through file system mounting, so it's transparent for you, but it'll make sure you can access the file system. And we can also talk more in detail about how distributed file systems work or how Kubernetes works. So in this example, we're going through local file systems, but the principle is very similar for distributed settings. And then once all the running is done, the user can read the outputs back from the file system and look at the log, or go look at the trained model, or look at the predictions that were made from inference. This is the kind of the whole flow in its entirety. It's a little complicated, but it's also a lot more simple than I've seen some models I've had to run myself. So this is kind of the core process of what will happen behind the scenes when you run that one line as a user. You call that one command line as a user, and then this is all done in the background for you. And the interesting thing is that it's actually relatively simple. You could basically go from 0 to a new runner in a weekend. So because it's effectively a few Docker calls, and we provide example code for this, you could have a runner going really quickly, and we're encouraging that. Like, if you want to make something that runs in MLCube, go for it. We do not insist that you use the MLCube library. We don't insist that you download our code and run our code and file issues against our repository. We would love it if you do, and we are more than happy to support you. But we by no means are here to push our code out on the world. We are here to show what can be done. And you can make your own in a weekend and add the features you want to see there. So let's talk now what we can do with this technology. And I'm going to showcase federated learning as a way to explain why all of this is useful. Like, why do we go through this MLCube things? Like, I've said it's great, but where does the greatness come? Like where it comes from is this idea in federated learning where a researcher wants to send their model to a hospital. This is exactly the thing we were talking about is researcher has model, hospital needs to run the model. And the reason the hospital needs to run the model and is not the researcher running the model is because the hospital can't send the data back to the researcher, right? The hospital can't, the researcher wants to classify cancer and MRIs. The hospital can't send those MRIs to the researcher, that's patient data. So the researcher has to send the model to the hospital. And so in this case, you effectively have multiple hospitals working together to train on their private data, but they're not sharing the data. And so this is exactly a place where MLCube can thrive. And MLCube by no means is federated. We'll get into the details later, but MLCube is not intended for federated learning at all. This is just one of our applications. And what's really happening here is that the MLCube federated learning combination starts like regular federation does. There's a researcher with a federated server, and the two hospitals are talking to the researcher. They both have their federated clients. Those clients talk to the MLCubes, which in this example, they're pulled from GitHub. And the key understanding here is that the hospital gets the federated client and the GitHub pointer from the researcher, and that's all the hospital needs. And so we're going to dig into what actually goes on within one hospital. Basically, you have a federated server speaking its protocol with a federated client. So this protocol is specific to the framework. OpenFL will have a different protocol it runs than any other federated framework. So this is specific to the federated service. MLCube is a regular MLCube. This isn't anything special. There's no special plugin for federated learning. This is just the same MLCubes we've been talking about with the same kinds of technology. And the way this interaction works is for the current federated round, the model will be sent from the server to the client. And then that model will be converted from the internal representation of weights and averages to a checkpoint, like a PyTorch or TensorFlow checkpoint. And then we'll do a normal MLCube invocation, pass it in. Here's a regular PyTorch checkpoint. The MLCube doesn't even know it's doing federated learning. It just says, oh, here's a checkpoint to start with. I'll do an epoch of training and then stop and produce a new checkpoint. That new checkpoint goes back to the client converts it back to what's needed for the federated protocol, and the process repeats until the model is trained. And the key thing to call out here is that the MLCube doesn't actually need to speak federation, and the FL client doesn't need to reason in great detail about the MLCube. It needs to know a few things like, do you want a PyTorch or do you want a TensorFlow checkpoint? But that's the extent. And if we look at what's actually going on here, it's that the federated cube takes in the institution's private data, the parameters, like the batch size and the number of samples to train on, and then the checkpoint we talked about, which came from the federated framework. And then it does a regular epoch or partial epoch on the private data. And then it produces logs, it produces metrics that the federated framework will pick up, and produces a new checkpoint that the federated framework will pick up. So this is in the same interface, same file system interface, same config files. This is a task called train within the MLCube. The MLCube doesn't even know it's being federated right now. And with the data coming in and the logs, metrics, and new checkpoint coming out, you have everything you need. And this is interesting. And we're doing this right now for FL because it solves some key problems. One is security is very important in federated learning, because the basic principle is that, these institutions, they have to work with each other, but they're very protective of their data, as they should be, because privacy is a very important thing, and every year it is more and more important. And understanding what they're running, what's going on, what it can and can't do is super important. And in this case, you have a clean artifact, a Docker image, an MLCube, that a hospital can audit. They can look at it and they can even see it doesn't need internet access. The code is never going to talk to the internet. They can see here are the files coming in. They can see here are the files coming out. It is super simple and super clean from a security perspective to understand what is going on. And that cannot be underestimated when you're dealing with HIPAA, when you're dealing with all these other considerations that go when, institutions that don't necessarily trust each other that much have to work together. Also, this is very easy to run, right? We talked about how it's a super simple setup, right? It's get me these config files and I'm good. It's pre-packaged. You don't have to have the hospital IT department debugging your Docker image to figure out why the Docker built on your machine, but now that Ubuntu updated their repositories, the Docker is not building anymore, right? Like, that is not helpful to anyone, right? It's pull the Docker image and get going. And it is very difficult for that to break. And that is critical when you're dealing with, people who don't want to spend their day debugging your code. And finally, as I said before, the model doesn't have to be federated intentionally. You don't have to think, now I'm making a federated model. You can just have it. And the feedback we got from these federated frameworks that integrate with MLCube, the integration into their framework, into their product, was 10 hours. This is, a weekend project, and you can have federated learning going with MLCube. So you can basically take, a day or two of your time and get MLCube running with an existing product or service, whether it's a workflow manager or whether it's an experiment manager. You can get it going super quickly. And this is because it's very simple and yet very powerful. And I just want to wrap up by saying, we're not a product. We're not here to sell you something. We are here to work together to make AI easier for everyone. We want models to be easy to work with, and we want to solve the frustration in the industry, and we want to grow AI for everyone. Overall, we would love for you to join our working group, mlcommons.org, or look me up and email me. I'm victor@mlcommons.org. You can join our working group, best practices working group, from there. If this has inspired you with use cases or integration ideas, definitely reach out. We're looking for people to collaborate with. We will be so happy to hear from you. And you can go to our GitHub, which will have examples that you can download and run that go through in detail what we talked about here. I really appreciate you, going with us to help solve this problem. And together we will make AI easier and take a big chunk of our time back to do more useful things than reading READMEs. I really appreciate it, and take care.